discuss the regional Boreal summer IntraSeasonal Oscillation predictability over Western Pacific and also over Indian Ocean. Now, another paper earlier published is the predictability study of the Boreal summer IntraSeasonal Oscillation as a whole. So main content consists of these two work. But before that, I want to discuss some background informations which may be useful for understanding. For the summertime intraseasonal oscillations, first of all, the OLR variability center shift from northern winter, which is in the southern hemisphere, to monsoon regions. And secondly, the evolution of the white phase start from here, moving eastward, bifurcate and form this tilted rain band, and then moving continuously eastward and northward, especially in the Indian and West Pacific regions. They also across the IPCC move to the Eastern Pacific and North American monsoon regions. So those three features are distinguished from the wintertime, the MJO prevailing features. Now, we know that, for example, because it propagates northward in the Western Pacific, if we monitor variability of OLR here, we are able to predict maybe 10 days or 15 days later in this monsoon trough region what's going to happen. And that can bring the predictabilities. For instance, when the ISO move from equatorial region to this monsoon trough, this total field shows strong monsoon trough, and the dot is the tropical cyclones. And during the dry phase, the monsoon trough disappeared, controlled by this West Pacific subtropical high, and the genesis and the TC activities are much less within this box. Now, this box is particularly the TC experiences of rapid intensification. Within 24 hours, they intensify by 30 knots. So you can see the white phase of IPO can enhance the intensification, and the dry phase does the opposite. So if we monitor OLR anomaly over the equatorial Western Pacific 3 pentad later, there are a lot of rapid intensification, 22 cases. And 8 pentad later, the dry phase is less than 5. So you can see there is a huge contrast. So even we monitor equatorial Pacific OLR, we are able to probably estimate the rapid intensification 3 or pentad later, or even 8 pentad later. So this is how the usefulness of ISO for prediction of the extreme event. Now, first thing, as a background materials, I want to discuss what is MJO and the BCSO. And basically, I would say that the intraseasonal oscillation has a very pronounced seasonal variations. The MJO is dominant winter time, and they're moving eastward mainly. But I think MJO BCSO has a distinct circulation structure and propagation pattern and life cycle. So that is why we need to consider summer, Boreal summer ISO or BCSO separately. And there is a paper by Kikuchi et al. To discuss the difference between the MJO and BCSO. And this is the principal mode of ISO during DJF and the JJA. And this is the first 2 UF, and this is the second. This is the first 2 UF for JJA. And for winter time, these two represent eastward propagations. But during summer, you see you have this tilted rim band structures one center is over Indian Ocean, another is over Western Pacific. So they are also represent propagations, but you see the structure, the propagations is very different. And because of this, therefore, it is useful if you project the, you think MGO has a two mode, bimodal. One is a DJF mode, and this is the extended UF analysis derived, and this is RMM index derived evolution. The RMM index is Wheeler-Hendon's. So during winter time, they are quite similar. And during summertime, they are also similar, except this tends to be stronger than the RMM index described. Okay. Now, because of the difference between BCSO and MGO, so it is possible that if we take a filter data to do JJA mode and the DJF mode, call this as MGO, this called BCSO. Okay. Now then, in the any of day, they can project to this two mode. So therefore, you can get a BCSO time series and MGO time series for each day of the year for 30 years. Then you can look at in which season the BCSO is dominant and in which seasons the MGO is dominant. And it is quite clear that from June to October, the BCSO, the red, is larger than this MGO mode. Okay? And because of that, you can see clear seasonal variations. From December to April, the blue MGO mode is dominant. And for May to October, and this BCSO are dominant. April, November are transition seasons. Both are coexistent. So that is why we really need to look at different seasons. Monitoring and measuring MGOs. For MGO, the Wheeler-Hendon's use all year round. They do not distinguish summer, winter, or spring. All year round, and make a two-dimensional OLR and 850 hectopascal and 200 hectopascal wind, multivariate UF along equator. This is average between 15 south, 15 north, and the first UF, second UF. So those two modes account for about 20% of the variance. Now this 20% of variance is considered to be most predictable. So this two UF together represent one MGO mode. So normally when the monitoring this MGO, they use this first two UF called RMM index. And they use RMM1, UF1, and UF2 spanned in a phase space. This means UF1 equals 0, and this UF2 equals 0. So it divided 8 phases in the phase plane. So each day has one dot. So you can see how they evolve. And the prediction start from here as a plumed, and this ensemble mean, trying to predict how the trajectory move in this phase plane. But this is good for meteorologists, but not necessarily good for public, because this phase plane, the interpretation sometimes could be very difficult for public to understand what's going on. Now, one of the problems is RMM does not distinguish seasons. So if you look at the NDJF, northern winter time, this is the OLR, frictional variance. And this is during the summer, northern summertime. So the maximum during DJF is this red curve, and during summer is that red curve. And they move tremendously. But the RMM tends to capture the variance in the equatorial regions. So what happens is this off-equatorial region, the monsoon regions, and in monsoon regions, they carry less frictional variance. Therefore, if we use this, does not distinguish a season, we may have difficult time to capture the monsoon intra-seasonal oscillation. So that is why we advocate another indices for Boreal summer intra-seasonal oscillation. And for this purpose, for example, we focus on this Asian monsoon regions using 850 zonal wind and OLR as two variables, make a multivariate UF analysis. Now this is the first two UF mode. Okay. Now this two mode, one has a dipole structure between Indian Ocean and West Pacific. Another is a tilted rain band, has two separate centers. So they are together represent some kind of northward and eastward propagations. But these two are not equal to each other. That means that in addition to propagations, there is a stationary component. If we use this BCSO1, BCSO1 means this UF1, EF2. This is the frictional variance they captured for OLR, and this is for zonal wind. And this one is the 2RMM, capture the frictional variance. So obviously this capture more frictional variance than RMM during the summertime because it's a locality. So that is the advantage of using this against using RMM during Boreal summer. Now the evolution of BCSO using the first two UF mode. This is a phase 1, 2, 3, 4. And you see the white phase develop over Indian Ocean and form this bifurcation of tilted rain band. This tilted rain band moving eastward and also slowly northward. Once across the maritime continent, it mainly moving northward, okay? Then disappear, go back to this phase. So this is how it evolve. So this evolving pattern is very complicated. It's different from the MJO. MJO is basically from west to east. So you can have the phase diagram showing this is the Indian Ocean, maritime continent, West Pacific, and so on and so forth. But for this, if you use this phase diagram, it's pretty difficult. So although the paper has suggested this phase diagram, but my own opinion is that this is not really very useful, even for meteorologists, because what in your mind is the movement is complex. It's very difficult to assign this is some locations, right? Indian Ocean and East Asia. What does that mean when you look at those dots? So there is an issue. I hope that we can resolve this in future. In other words, we communicate with the public and even with meteorologists. We want to show this type of phase diagram rather than this in the phase plan. But how to do it, I think we have to think about a smarter way or better way to present. But anyway, this phase diagram I think has its weakness. Now, the predictability study so far focus on this predictable mode. This RMM represent MJO mode and the BCSO mode. So because this part is supposed to be most predictable. And remember that even this two part is only 20% the frictional variance is not really much, okay, for a single variables. So let's talking about this predictability, the concept, methodology. So what is predictability? I think last year I was here, briefly mentioned this concept. This is from National Research Council, the science report, assessment of ASI prediction. It says to what extent, the extent to which the process contributes to the predictability quality. Now this extent called predictability. Literature provides variety of interpretations. The committee agreed to only a quantitative approach. Okay. Now they also explained some aspect of the committee's approach. For example, quantitative estimate the upper limit of predictability for real climate system are not possible. So sounds very rigorous, but pretty pessimistic. Verification of the forecast provide a lower bound for the predictability. And this statement is useful. In other words, if you have a model make a prediction and the prediction skill is there, so this could be a demonstration of the lower bound. Traditional prediction studies, for example, trained model studies to look at the error growth are qualitatively useful. Now, I want to discuss aspects of the predictability. Now, first of all, we have to keep in mind that the prediction of future climate states can never be perfect at any lead time. Therefore, the predictability is a measure of the uncertainties that limits the accuracy of the predictions. So therefore, you see the predictability and uncertainty are closely related. So useful prediction must include information about the predictability, in other words, about the uncertainty. And more importantly, we should realize the predictability is a function of state variables. For example, temperature, winds, precipitation. They all have different predictabilities. Precipitation is very low, and winds, temperature may be higher. Okay. And also, they are spatial dependence, and also the forecast lead time dependent because of error growth. So for given variables at any given space, the predictability decreases with lead time. So therefore, this gives a possibility that you can measure predictability, use the maximum lead time. At that time, the prediction becomes meaningless. And predictability can be estimated, although it's not perfect. We have to be more proactively to pursue, to estimate those predictability. You can use observational data, but they are limited by the length of the record. Normally, it's very difficult. For weather forecast, maybe okay. You have 10,000 of the cases. But for climate prediction, it's very difficult. However, you can also use prediction tools, something like a model system. And the predictability using model system is model dependent. We all know this. Therefore, you can call this as a practical predictability. And predictability may be viewed as a limit of the predictability when the model system approach ultimate perfectness. Okay? In other words, when the models improved, the estimate of predictability will be more accurate, more close to the real climate system. So, so the optimum model system, of course, is a coupled climate model. As a whole, we have to emphasize this. The GCM, coupled GCM, is an ideal tool for this. So the methodology for estimation of predictability, suppose we take MJO mode as examples. Now, we have to assume our model is perfect. That is why the estimate is a practical predictability, because the model error can affect your conclusions, but there is no other way. You have to assume the model has no error first, then improve model, so improve your estimation time by time. Now use the perfect model assumptions. There are two ways to, one is a single member estimation, another is ensemble estimation. Now the difference is that if you do ensemble predictions, you can take any of the single member as ground truth because you assume the model is perfect. Therefore, any other members different from your designate truth is error growth. So you can estimate. This is called the single member estimate. Now, you can imagine that this will give you a shorter predictability limit because you use single members. And the ensemble estimate means that you take one of the member as a truth, as a realization, and all other ensemble members you make ensemble mean. Then look at the error growth. And in that way, actually you can get the longer lead time for predictabilities. So I think that although both has been used in the literature, but this one is more reasonable because we are doing ensemble forecast anyway. So our prediction is made by ensemble mean rather than each of the single member. So therefore, in the following, I will emphasize this ensemble estimate approach. Now, first of all, for Boreal summer IntraSeasonal Oscillation, you need to calculate BCSO index, this UF1 and UF2, following this Lee et al.'s paper. And that paper use OLR and U850 in this domain. Okay. Now, so we focus on the only PC1, PC2 to get this index. Then we estimate the predictability and the prediction skill of this index. Okay. To estimate the error growth, you have one member assigned as a signal. Okay. Now the other ensemble members you consider as a predictions. Okay. Now they have error, of course. Suppose you have a 10 ensemble. You take one of them, then the other 9 as a predictions. You can make one forecast to look at the error growth. You can take the second members at the remaining 9 as ensemble predictions. So you can get actually 10 different predictions, and each of them has a different trajectory. So you can estimate the error, distinguish the error and the forecast to look at their spread. So if this is the signal change with time, this MJO signal, and this is the error growth, so to someday there are the error is as large as your signal, then it says this is the predictability is about 20 days. Okay. This is the basic idea. The model we have used to look at is this SV experiment, where this APCC is one of the sponsor. So we collected about 10 different models worldwide. Now next I want to discuss this predictability BCSO first. Okay. As I said before, this is the first 2 UF describe this movement. It's idealized BCSO. The model we used is 6 models because they have roughly the same length of predictions, so it's easier to handle. As I said, I have discussed this observed BC index, what it is, and how these 2 modes together represent the movement. Now, let's look at the BC index prediction skill and predictability. Now, prediction skill and predictability is similar because prediction skill is just to use ensemble mean forecast, validate against the observations, and the predictability is to variate the ensemble mean forecast error against one of the members, taking one of the members as the truth. So the procedure is very similar. So we can look at, this is from individual models, I think 1, 2, 3, 4, 5, 6, 7 models. This is actually from Nina et al. It's for the Wheeler-Hendon MGO forecast results. Okay. Now, the black curve here is the scale, the single member prediction scale, and this is the ensemble mean prediction scale for different models. And this is the predictability estimate for single members, and this is for ensemble mean estimations. So I'm more toward this ensemble mean approach. In other words, the MGO predictability in terms of the first leading mode could be up to 40 to 50 days. But the current, I think, prediction skills are quite limited. And I think this is from 20 days to 25 days. A good model maybe up to 25 days. Okay. There is a large discrepancy between the models. So for BCSO, we have to look at the strong initial condition and the weak initial conditions because we think they may be different. Okay. Now the strong BCSO initial condition is in the initial day, the PC1 square plus PC2 square, the amplitude greater than 1.3. Okay. Now the weak is less than 1.0. Suppose initially the amplitude is small and large, and to see the prediction scale and the predictabilities. Now it turns out that the predictability and that does not really distinguish this weak and the strong case. Both are close to each other. Okay? But the prediction skill is highly depends upon the weak and the strong one. I will show you later. Now this is the dependence on the initial amplitude. This is predictability estimated by the ensemble mean approach. This is prediction scale. Again, is ensemble mean scale. And this is strong initial condition. This is weak initial conditions. As I said, for this predictability, they are quite comparable, but prediction scale, this is something like average is 21 days, and those are only 12 days. So the prediction scale is quite depends upon the, I'm sorry, this is 22 days and 16 days. So prediction scale for those strong initial amplitude will be higher, but the predictability about the same. And it also depends upon the initial phase, but we try to use different initial phase to see how is the predictability predictions. And the results is that there is no systematic predictability dependence on the initial phase. Maybe our sample size is not large enough, but anyway, and we couldn't find this phase dependence. And this is one of the interesting results. The initial season, in other words, each of the month, suppose you start from May, June, July, August, September, October. Now we find that there is some dependence on the particular month. Okay, so the estimated predictability prediction scale vary actually in each model with the initial month, but systematic season dependence is not found across 3 models. And I think the only thing is in the August, they showed some difference. Let me see, the August, which color is August? The green color, I think, is August. So there are some spread. August, the green. Yeah. Yeah, some model actually show that their difference, but is not really prominent. Sorry, I think I couldn't find the August difference. Then we look at the dispersion of the initial ensemble and prediction scale improvement. This is very, very important because the initial ensemble's dispersion depends upon your forecast system. Okay? Now, if you make if you make a better ensemble dispersion, then they could affect your prediction skills. Okay? Now, actually, they found that there is a relationship between the spread and also the scale improvement. So if the initial ensemble spread is smaller, then the improvement actually is higher, right? So the ensemble mean prediction scale could be significantly improved by well-dispersed initial ensemble forecast error. Okay? This is spread minus RMME. So to summarize, we use a 6-couple model handcast data in the ASV project, and the predictability estimate and prediction scale are examined. The multi-model mean predictability estimate and prediction scale for BCSO with strong initial amplitude are 45 days and 22 days. This is scale. This is predictability. And those numbers are comparable with MGO, Nina et al. Has assessed for Boreal winter time. The significantly lower BCSO prediction scale compared with its predictability, because this is a large discrepancy, really suggests there is a room to improve the dynamic BCSO predictions. Also found the predictability, the estimate predicted is independent of initial amplitude. However, the prediction scale we found is strong initial amplitude is 60 higher than the weaker initial conditions. The BCSO predictability prediction scale are slightly phase and season dependent, but the degree of dependence varies with models. So there is no common conclusions can be made regarding the seasonal dependence. The last point is the prediction scale depends on the method that generates ensembles. Our analysis indicates that a better dispersion of ensemble members can considerably improve the ensemble mean prediction skill. So the regional BCSO predictability over Asian monsoon regions. Now the motivation is that we want to design those index which can capture more frictional variance. As we said before, if you use the BCSO index, they can capture more OLR variance. But if you ask the question, is this enough, or can we do better than this? Now, apparently, the first thinking is the Indian Ocean and the Western Pacific, the evolution, the movement may be different. So we should consider those regional difference to see whether we can find a better representation of the regional indices. So therefore, start from this, we really want to compare, first of all, the regional BCSO features over the Indian Ocean sector and the Western Pacific. Then to derive maybe regional indices and to see how these regional indices compare to the BCSO indices and to see whether they can capture more frictional variance. If they do, then we want to estimate those regional indices predictability and prediction skill in the current models. Okay. The final purpose, of course, to improve monitoring and the prediction of BCSO, because how to do this still an open area. Now, if we divided this Asian Australian monsoon domain to Indian Ocean sectors, the division line is 105 degree east, and this is the east part, which is the Western Pacific. Okay. Now, you see the first two UFs capture more frictional variance than the BCSO index as a whole. Okay. The BCSO index previously we see the capture lower. This is a combined OLR and zonal wind. And this domain is slightly larger. Later on, we will compare in the same domain. So if we compare the same domain, we have to project to each grid point. Now this is the OLR, and this is U850 hectopascal wind. And this is the BCSO index capture. And this is the combined Indian Ocean and the Western Pacific index. In other words, over the Western Pacific domain, we use West-North Pacific ISO index to count how much friction variance. And in the Indian Ocean sector, you use the Indian Ocean ISO index. But add them together, still can compare with this BCSO index in the entire domain. Now, you can see the RMM, if you don't distinguish season, they capture less. And this one is better, but obviously this regional indices capture more. So is the 850 hectopascal wind. So that we thought that increase of the frictional variance captured by the index is very desirable when we look at the predictability and prediction skills. Now this is also a comparison of the frictional variance captured in this monsoon domain, but it is for the daily data. This combined ISO West Pacific regional index capture 10%, and this is 7% for BCSO index, and 5.3% for MGO index. For the U850 hectopascal is also is generally much higher than this. And again, this regional indices is better than the other two. And this is the longitudinal distribution of the frictional variance. And you can see this monsoon region around 10 to 30 degrees, this RMM was not able to capture much. They mainly capture the equatorial regions. But for the regional and the BCSO index, they capture larger amount of frictional variance in the off-equatorial monsoon regions. So this is compared to daily frictional variance. Now if you compare to the filtered intra-seasonal band, now this combined regional indices capture 15% or 23% is much higher because the denominator now is reduced. Okay. Now if we further divided this to 10 to 25 days, the biweekly mode, and this is the 25 to 70 days, more like intra-seasonal time scale, this 2 time scale. You see again, those regional indices capture more frictional variance than other two. Okay? Now this is if we use the pentad mean to calculate how much the frictional variance, I think this makes more sense because when we do this intra-seasonal forecast, we are not really to predict day-to-day variability. Rather, we probably want to take every 5-day mean to make predictions. So what is the pentad mean variance? Pentad mean variance, of course, is much lower than daily variance. Therefore, the predicted two regional indices account for 17 and 35%. Okay. This is what we expect, that if we do the regional indices, it probably can capture of this amount of pentad mean variance. Okay. So comparison frictional variance shows that the regional difference has advantage use the regional indices. Now, for these two regions, if we look at their spectrum, you see some difference. In the Indian monsoon region, the Indian Ocean ISO index is mainly 30 to 50 days peak. But in the Western Pacific, you have this 30 days and 6 days. You also have this biweekly 10 to 20 days peak. Okay. Now both for the PC1 and the PC2, you have this biweekly component in the Western Pacific. So in other words, the biweekly component has relatively important contribution to the West Pacific region, but less contribution to the Indian Ocean regions. Another difference between this Indian Ocean and the West Pacific is this seasonality and their interannual variability of these PCs. Now, what we have compared is this PC1, PC2. This two is the regional indices. And compare, also look at the PC3 and PC4. But this is relatively less important. Let's focus on the first PC1, PC2. In the Indian Ocean, the PC1 suddenly increased during May, then gradually actually decay. And the Western Pacific PC1 has a major peak in the August. Okay? So the seasonality is very different. And for PC2, Indian Ocean has a double peak, but the West Pacific has a single peak. So you see the regional difference, and because the regional difference, if you link them together as a whole to derive the speciesal index, you cannot capture those regional characteristics. Okay? Now, this is the year-to-year variability. Look at the PC1, okay? Interannual variability. The variance in May to compare the two regions. And interannual variation, I think you see the difference between these two patterns. Okay. So in other words, if you look at the year-to-year variabilities, the PC1 is also different. Not only seasonal variation different, but also year-to-year is different. This is an example in May, that example in August, and you see their interannual variations basically is not correlated. So this is, gives us a clue that the regional difference is important. Now look at the life cycles, and the Indian Ocean ASO life cycle and its seasonal preference. Now this is the 8 different phases according to this first 2 UF mode. And if you just focus on this Indian Ocean regions, the box regions, you see predominant northward propagations. And that mode project to the Western Pacific is pretty small. So it's basically saying that if you focus on the Indian Oceans, what you see is dominant northward propagations. And the phase 1 has a large loading in the October. And each of the phase actually has their preferred, the month is not uniform across the 5 months. Okay? Some phase may be, but some phase is very distinct. This type of pattern is occur during July. So that gives you a feeling about those different phases can be preferred in a specific month. Like this, prefer in October, this prefer in July. Okay. And if we focus on the West North Pacific regions in this box, they have less projection in the Indian Ocean. So that means really the regional difference we should focus on. Okay? Now, in the Western Pacific regions, again, you see prominent northward propagation is dominant. You see some of the eastward propagations, but not as prominent as you look at the entire Asian Australian monsoon regions. Okay. Some of the predictability study, if we focus on the Indian Ocean and the Western Pacific separately, so again, very similar to before, to define this weak and strong initial amplitude. So we see that the predictability for strong and weak initial conditions, there is in our Indian Oceans looks like a strong initial amplitude corresponding to also higher predictability. But whether this is statistically significant is very difficult to determine because the sample size is not really large enough. So there are some differences in the West Pacific as well. But keep in mind, this may be due to the sample error. But in any case, the difference is not that large. But if you look at the prediction scale, however, they are double. Okay? In other words, no matter in the Indian Ocean or West Pacific, the strong initial amplitude gives you much higher scale than the weak initial amplitude. And this is basically summarized in these figures. Okay? Now this figure actually is summarized by that. And what about the initial month? I should say initial month. And now this is all summer initial conditions. Okay? And this is different models. We have looked at, I think, 3 models: CMCC, European Center, and Australia models for these two regions. And the PC1 scale and PC2 scale is different color. The combined scale is this black curve. So for Indian Ocean ASO, the combined scale, okay, is about 8 to 10 days. ECMWF is much better, about 15 days. And this model is about 10 days. So there are large difference. So, but the best model estimate over Indian Ocean and the West Pacific is about 10, 12 to 15 days. This is the prediction scale. And this is in terms of the regional indices. Okay. Then, if you look at the different months, this is compared with May, July, and September, 3 different months, the initial conditions. So you see the May seems has better prediction scale in the Australian models, but in the European Center's models, slightly better than the other 2 months. Okay. Now, in general, I think May probably has better prediction skills than the other month, and so in order to capture BCSO better, we look at the spatial temporal structure of Indian Ocean West Pacific, examining their corresponding leading mode. Okay. Now the combined, this index, as I showed, can capture more of the variance, okay? About 30% of the daily OLR, daily U850, 10% daily OLR. Now, if you look at the pentad mean, this is much higher, okay, than this value in these 2 regions. Okay. Now, this value is about double this MJO capture variance, and 50% higher than the BCSO index capture. So this sounds to be a good measure if we take this regional indices to look at the prediction scale and the prediction and the predictability. Now, there is a regional difference between Indian Ocean and the Western Pacific. The Indian Ocean mainly is northeastward propagations, and the dominant energy peak is 30 to 45 days. And their PC1 has maximum variance in May, but the West Pacific propagate northward mainly, and has a broader spectral peak, include both quasi-biweekly and ASO, 25 to 60 days. And the PC1 has a maximum variance in August. So those regional difference is is very significant. Okay. And if you look at the year-to-year variability or decadal variabilities, you found this Indian Ocean and the Western Pacific is also different. Now, the several phases of Indian Ocean, West Pacific show different seasonal preference. Okay. For example, Indian Ocean, as I said, the PC1, or the phase 1, prefer in October, and phase 2 is prefer in July, and so on and so forth. Not every of the phase has seasonal preference, but some of them does have. The multi-model mean estimate predictability is 40 to 45 days for the Indian Ocean ASO. And for the Western Pacific is 30 to 37 days. Now, the reason of Western Pacific lower than Indian Ocean, I think, is because they have this component of biweekly mode. And those biweekly mode, because the periodicity is short, therefore their predictability is also shorter. So compared to Indian Ocean is more of 20 to 45 days. So their predictability is higher than in the West Pacific. The multi-model mean prediction scale is significantly higher than with high initial amplitude. So it's about 20 days for the two indices. But the weak initial amplitude is only 11 days. Okay, this is the